Hello, this is our lesson on solving an inequality. We've already done equations and now we're going to move on to an inequality. And what we're going to look at first is just what is the basic difference between an equation, I've got 2 on the left, the x equals 10 and the 3x equals 12, and an inequality where you have the less than and or the greater than signs. So I'm just going to look at the first two. When we say x equals 10, that literally means 10 is the only answer that works. So if x equals 10 and you plug it back in instead of the x, you get 10 equals 10, and that's correct. Any other number and you plug it in, say an 8, and 8 does not equal 10, so that doesn't work. I mean, this is the simplest type of equation that we basically have. When you graph it, because x does equal 10, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then on the 10 spot, you just put a dot to show that 10 is the only answer that exists. However, with an inequality, you're not saying it equals 10. You're saying on this particular one, x is less than 10. So if I actually tried to put in a 10 there, it doesn't work. 10 is not less than 10, so that would be incorrect. So let's think of a number less than a 10. How about a 9? And now we've got 9 is less than 10, so a 9 works. But so would an 8, so would a 7, so would a 6. Even if I decided, okay, let's go all the way down into some negative numbers. How about negative 3? And yes, negative 3 is less than 10. We're making true statements here. But because there are so many that work, anything literally less than a 10, this also includes numbers with decimals like 9.5, 8.2, 7.336. Any of those are less than a 10. Because there are so many, there's just not one number that works, not one number that makes it true, but a whole bunch of numbers. So when we graph it, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to put some over here. Okay, we go ahead and we circle the 10. Now this time I'm not going to shade it in like I did before. We don't shade in the circle because there was no equal sign with the x is less than 10. It was just a less than. The shaded in circle would indicate that it was equal to 10 like on the other one. But if I did put in a underline here, like that, then that would be x is less than or equal to 10, and you would go ahead and shade in the dot to indicate that the equal sign was a part of it and that 10 was actually part of the solution. I'm going to go back to the way it was before. So it's just x is less than 10. And just like the shading showed that x was a part of it, shading, or the 10 could have been a part of it, the shading also shows which are the solutions. So in this particular one, since it's all the numbers less than a 10, I would shade everything less than 10, so on the left. And to show that it keeps going, I would like shade an arrow. This means that all the numbers less than 10 are a part of my solution. Now those are, like I said, the very simplest types of equations we have. There's nothing really even to solve, just to sort of understand the difference between an equation and an inequality. An equation has like one answer, these types of equations, and an inequality can have many answers. Well, let's look at solving one down here. Okay, so I'm going to start this the same way. Now, your DCID steps, divide, combine like terms, and isolate all apply, and there's no, excuse me, not divide, distribute. There's no distribution on this one. There's no combining like terms, but we do need to isolate. We've got to get the 3 away from the x, and this is where I was thinking about dividing, because we would divide. This is 3 being multiplied by an x, and the opposite of multiplication is division. We have to do it on both sides. So 3 divided by 3 is 1, so we end up with 1x, and 12 divided by 3 is 4. So I get 1x equals 4, but then 1x is the same as x, so the 1 can just become part of my box. Now what that means is that x equals 4. 4 is the only number that exists that's going to make this equation work. If I take my original equation and instead of the x, because now we're saying x is actually 4, put a 4 into its spot, And then use my order of operations. I need to multiply. 3 times 4 is 12, and 12 does equal 12. That works. It balances. It makes a true statement. So 4 is the solution. But if you put any other number in there, like a 5, you'll get 15 equals 12, which doesn't. So it doesn't work, and the only solution is a 4. Whereas on this next one, it's basically the same thing, except for now we've got inequality, but you solve it the same way. Still have to get rid of the 3. You still have to use opposites, so it's multiplication. 3 divided by 3 is still 1 with the x. In this particular instance, we're going to bring down the sign. You don't always do that, but right now that's what we're going to do. And then 12 divided by 3 is 4. So I get 1x is greater than or equal to 4, and I can just say x is greater than or equal to 4. And we already know if we put the 4 in, we get 12, so that works, because 12 is greater than or equal to 12. But let's pick a number that's bigger than 4, like a 5, and see if that works, because we're saying it's greater than should also work. So in place of the 4, place of the x, I'm going to put a 5. And then I'm going to work it out. So 3 times 5 is 15. And 15 is greater than or equal to 12. So we can see that that works. A number greater than 4 worked. If I try to put it in a smaller number than a 4, like a 3, then I get a 9, and that won't work. 9 is not greater than or equal to 12. And when we graph these, I've already got the 4 graphed. You would just put the dot on it like before. But when you graph this one, 0, 2, 4, okay, and I'm going to do a few more. You're going to circle your 4, but this time we're going to do a closed end dot because we do have the equal sign. And you're going to shade to the right to show that you're talking about numbers greater than or equal to 4. So 5 is a solution, 6 is a solution, 7, 8, you can just keep going. But also 4.1 is a solution, 4.2 is a solution, just anything greater than or equal to a 4.